Good evening, ladies and gentlemen, and thank you very much for inviting me. I'm delighted and very honoured to be invited by the engineering group to deliver this lecture. I'm especially honoured by the fact that there's so many eminent engineering geologists have gone before me, as you've seen on the screens, as you were coming in. Thank you very much. I hope you will find what I'm going to tell you very interesting and useful. It's a broad topic, and I'm not going to go into things in too much detail. I'm going to tell you about mud rocks and hopefully acquaint you with some of the problems they can pose in engineering and how these might be avoided, given information about how they were formed, what they consist of, and what structures they contain. I hope that through this knowledge, costly mistakes and even fatalities will be avoided. I'll start by explaining the manner of the formation of mud rocks and how mud becomes converted into rock. I do this as a background to the processes by which the rock then degrades back to mud. Because durability is what causes many engineering problems, most of the rest of the lecture is devoted to rock to mud, including problems due to the oxidation of pyrite in particular. I will outline some of the examples that cause rapid deterioration in the properties of some mud rocks and the presence of pyrite, and also alert you to problems with the standard that specifies the quantification of pyrite in rocks and soils. I'm forgetting to advance this thing, sorry. You can see that what I've just explained is on the screen now. Mud rocks are fine-grained sedimentary rocks composed of silt-sized materials, less than 63 microns in size, along with clay minerals. But different standards don't agree about the exact definition of the different types of mud rocks, which can lead to confusion. Because of their small grain size, it can be difficult to determine that size. Mud rocks... That's the slide. Take it on. Sorry. Methods are available for soils that can be easily disaggregated, but it's more challenging for rocks in which the grains are bonded together. There is advice in the literature, and a good place to start would be Chapter 36 of the Manual for Geotechnical Engineering, which has recently been revised. Mud rocks occur in engineering because they're the in situ material in slopes and other situations, and may suffer various forms of instability in slopes. Weaker mudstones erode more rapidly than interbedded sandstone or limestone beds, as seen in the slides at the bottom of the slide, and also the bottom right, which are examples from Sheffield and Scarborough. In the case of the Scarborough one, in the bottom right corner, lumps of limestone have fallen off that cliff and hit the shelter that you see because of the weathering of Oxford clay, which lies underneath it. In some cases, the mud rock might be a very minor part of the sequence, such as the slide on the left-hand side, which shows mainly limestone, but there are thin seams of mud rock between these limestone beds, and because of the weathering of the mud rock, what it looks to be a very stable slope will become unstable in a couple of years. In some cases, the mud rock is the majority material. The slide at the top right shows Speaton clay in Yorkshire. The failed material rapidly degrades into mud flows that spill onto the beach. Further examples of failures due to mud rocks. In this case, the formation, this is the slide on the right-hand side, where a formation called Gault clay lies beneath the chalk between Folkestone and Dover, means that the railway line is built over unstable land. Again, erosion of the failed material is a problem. Other coastal problems are shown on the slide in North Yorkshire. In some cases, there are interbedded layers of mudstone and sandstone And in the case on the left, the bottom left of the slide, the material has become unstable a few years after construction. The bedding of the sequence is towards that excavation. Sometimes problems occur in underground construction, where excavatability of the ground and the support of the excavation are important. Some mud rocks contain stronger materials that can be difficult to excavate, so unsuitable methods of excavation is used, or the support for the ground is inadequate, leading to the collapse of the excavations, or even worse, where it reaches the ground surface. In other cases, the excavated material can degrade rapidly during the excavation process to a slurry, which is then difficult to remove from the excavation, slowing down the tunnelling operations. In this case, slurry had to be taken out of the excavation by the, I do apologise, had to be taken out of the excavation using handwork with skips, which greatly delayed tunnelling operations. Sometimes mud rocks are used as the construction material, such as in embankments, dams, landfill cells, and infrastructure projects, and they serve as the in situ material for shallow and deep foundations. It's necessary to know their geotechnical properties and their performance as fills. Some types of mud rocks are prone to shrink swell behaviour, such as we see in the Oxford clay on the right-hand side of the slide. Due to the presence of swelling clays, the Amtil clay, which is the case at the top of the slide in the centre, has degraded to mud very quickly after excavation of this cutting. It's about a year old. And because the clay contains pyrite, calcium sulfate crystals, known as selenite, have formed. The weakening of the clay has resulted in high sulfate conditions, which will have to be taken into, which will have an adverse effect on the later stage of this project. I already mentioned that thin seams of mudstone can be difficult to spot in borehole cores, but it can also be difficult to investigate mud rocks. Boreholes may not recover intact core. Ironstone in the mudstone has caused the material to degrade in the upper box that you see here. And there's a loss of core, so we don't actually know what sort of material is there. The mud rock has degraded and been lost in the drilling flush. And stress relief effects in the lower core on the removal of the rock from the ground has caused it to fragment in this way into small discs. And of course, if you're trying to measure the strength of the material, it's not possible. Now, mud rocks occur widely in the UK. There are several major over-consolidated clay formations of Eocene, Cretaceous and Jurassic age in southern England, across here, and older Triassic and Carboniferous deposits underlie large areas of the Midlands, South Wales, the north of England and central Scotland. And of course, there are many cities and other urban areas on these deposits. Infrastructure routes cross them also. I should point out that not all these formations are predominantly, although all these formations are predominantly mud rocks, they also contain other rock types. And the non-rock mud rock formations shown here, just in blank, may also contain some mud rocks. And as I mentioned, these might have a significant impact on the behaviour of the rock mass. This is the surface outcrop of mud rocks in the UK. This shows the distribution of Oxford clay beneath later deposits. The blue shows where it's shallower than 250 metres, and the brown where it's deeper than 1,602 metres. I need to start my explanation of mud to rock by saying something about mud. This is derived by weathering processes on land. The nature of these processes depends on the climatic conditions, but basically There are physical processes that result in the fragmentation of rocks and soils exposed to weathering action, and chemical processes that change the mineral constituents through interactions with atmospheric gases and water. These chemical changes may result in the generation of ions in solution, which then get carried away, and also in the conversion of various minerals like augite, feldspar, olivine, and so on, into clays of different types depending on the weathering conditions. The different constituents are then transported by water, wind, gravity away from where they were formed, and these then will be deposited either on land in lakes, estuaries, and floodplains, or in the sea. Calcium carbonate derived from algae or shells and bones of organisms may also be deposited along with this material. This material may then be buried underneath later deposits, which bring about an increase in temperature and pressure conditions. And as I shall explain in a minute, increased pressure and temperature results in the conversion of mud to rock in diagenetic processes. These changes occur at a lower temperature than those of metamorphism. Tectonic forces within the Earth's crust may result in the formation of folds, faults, joints in the sediment, and these may be converted into metamorphic rocks or melted to form igneous rock. But in the case of sedimentary rocks we're talking about, uplift has occurred to form land so that the overlying deposits have been eroded away and eventually they become subject to weathering action. Burial and exhumation of these deposits might be over very long periods of time, hundreds or thousands of billions of years, or it may be over a much shorter time, and it may occur in repeated phases of burial and exhumation. The loading and unloading of ice sheets during the last glacial periods and the effects of periglacial conditions, the freeze-thaw action, may also impact on the properties of these materials, soils and rocks, and the structures that they contain. I also need to talk about a little bit about clay minerals. Clay minerals are platy in shape and formed out of in a sheet-like manner. They consist of layers of silica tetrahedra, which are formed out of one silicon atom and 4 oxygen atoms. In a sort of tetrahedral arrangement, forming a sheet. The other basic unit are octahedrally coordinated aluminium and hydroxyl or water atoms, ions. These are formed into sheets and configured in different ways in the different clays. I'm just going to mention three different sorts of clay. I'm going to talk about kaolinite, illite, and smectite. These all have a sheet-like structure, so that the clay particles are flat, platy in shape, and consist of layers of silica and made up of silicon and oxygen tetrahedra, and the alumina layers. In illite, there are 2 tetrahedral layers and 1 octahedral layer, and these are bound to adjacent similar layers via potassium atoms and hydroxyl ions. In the case of smectite, you have the same sort of basic structure, but the binding between the plate, the sheets, is via various cations and water molecules. The amount of water and the concentration of the cations depends on the situation. So it's variable, and it means that the smectite crystal can shrink and swell depending on the chemistry of the water. in order to balance the charges within the crystal. So smectite is a mineral which will shrink and swell in response to changes in chemistry and also in response to changes in water content. Clays exist in a hydrated state, and they then will, they are surrounded, they have negatively charged surfaces and become surrounded by water and cations in a diffuse double layer. This attaches them to adjacent clay particles, and it's what gives clays their plasticity. Again, the thickness of this layer depends on the chemistry and the concentration of the cations in the structure. So there are many factors which go to making up our mud rock. In the deposition, there's a large number of factors that affect the composition and structures of the material. And there are also processes that cause changes to the newly deposited material. For example, in anaerobic conditions, bacteria remove sulfate from the pore water, which leads to the formation of pyrite, which is an iron sulfide mineral, in the sediment. And organic material will be preserved in the sediment. Marine organic-rich mud rocks usually contain pyrite, whereas in fresh water it's likely that iron carbonate, otherwise called siderite, will be present as cement. Due to changes in the environment of deposition, both pyrite and siderite may be present in the same sequence of rocks. As I mentioned, the motivation for studying mud to rock was to aid our understanding of the bonding that holds mud rocks together. The first study I'll mention was carried out by Maurice Trevco. He carried out detailed studies of 49 different UK mud rocks ranging from Cambrian to Carboniferous in age with different states of induration. In these, the composition, rank, and by this I mean the diagenetic rank, in other words, the temperature that it was raised to during burial, the texture, some geotechnical properties and slaking behaviour were determined. One of the objectives of this study was to assess the value of using index tests. In other words, simple tests for assessing the durability of the materials without the use of sophisticated and technically demanding mineralogical, chemical and textural studies which he performed. I need to say something about diagenetic rank. And there are basically four main ways of measuring this, and it was one of the things which we needed to do in this study. One of them is vitrinite reflectance. As organic material is buried, it loses volatiles and it becomes more reflective. And therefore, this gives you a measure of the extent of the temperature to which it's been raised during its burial. The other way is to look at the shape of the illite smectite peak on the XRD trace. This shows a series of XRD traces for materials of increasing crystallinity upwards. The least indurated, the lowest ranked materials will have a mixture of illite and smectite, which gives a very broad peak on the XRD trace. As the diagenetic rank increases, the peak gets narrower and it gets taller as the ordering of the crystal becomes greater. And this can be used as a means of determining the diagenetic rank of the material. The process of conversion of illite to smectite releases water and cations into solution, and these may combine to form new minerals and cements and augmentations to existing minerals within the rock. And this change from smectite to illite does depend on potassium being available in the system, and it is also affected by the presence of organic matter and carbonates. The diagenetic changes which occur in the material are illustrated on this diagram. What happens to mud when it's buried beneath later deposits? The various constituents of muds, the detrital material and also the clay minerals, react to the fact that they are under greater pressure and temperature. And this shows the effects down to a depth of about 10 kilometers. At this sort of depth, the material will become recrystallized and the rock will be created into or changed into a metamorphic state, a slate or argillite, depending on the stress conditions. But at shallow depths, there are diagenetic changes. The heat and pressure cause smectite to be converted to illite, as I've just said, and this will be completed at a depth of about 6 kilometers. It is accompanied by the reduction in water content as the porosity is decreased and the interlayer water is removed. Pyrite and other diagenetic minerals will increase in grain size in response to the movement of ions in solution, and calcite and other cements will fill pore spaces, bonding the grains to each other. Organic matter in the sediment will lose volatiles, which will make it more reflective. And as I said, this can be used as a means of determining to what depth the material has been buried. Water and porosity decrease with the loss of water from the mixed layer clay and smectite, and there can be further reductions in porosity, pore size, and also pore volume during this process. Besides the mineralogical changes I've just described, there are structural changes with grains compressed and forced into contact, resulting in pressure point solution and the release of ions into solution and bonding of grains. This can result in the alignment of platy clay minerals and orthogenic growth of minerals and the formation of cements. This produces groups of cemented mineral grains, and eventually the creation of a skeletal framework of bonded and cemented grains will be formed. If the rock is quartz or calcite rich, the grains will become bonded at points of contact, making a strong, durable material. In clay-rich rocks, the bonding will be slower to form, and the clay is likely to be oriented perpendicular to the major stress, which in this case will be vertical, making the material anisotropic. This just summarizes the effects of burial. There are physical changes as well. During burial, compaction with void reduction and mineralogical changes. Because grains are distorted, the material retains stored strain energy because of the compression. Some depositional features and structural flaws will have been lost in the process of the mineralogical changes. Smectite and mixed layer clays are converted into illite, so making the material less prone to shrink swell. Cemented clusters of grains form, and there is a transition to a continuous framework of cemented grains and filling of pore space. The loss of swelling clays, structural flaws and porosity, especially the reduction in pore size, means that the material is progressively stronger, less compressible, and more durable. These changes can be seen in scanning electron microscope view pictures and illustrated here. We can distinguish between compaction mud rocks, in which there's very little cement, and cementation mud rocks, in which the material is bonded together by mineral cements. The length of time they are buried for also has an impact on the extent of diagenetic changes. Apart from the clay mineral alignment, the silt particles, the mainly quartz and feldspar particles within the material, may also be flattened by distortion and enlargement in their size, which will occur preferentially by growth in a horizontal direction because of the vertical stress. And this makes them more platy in shape, making the material more anisotropic. The effects of the changes can be seen by the reaction of placing dried samples of the material in water. where a non-indurated compaction mud rock will degrade rapidly into individual particles, whereas the cemented types will disintegrate into flakes, chips, or chunks, depending on the cementation and the presence of weaknesses in the mass, which relate to the mineralogical and structural features that can be seen in the SEM images. This is a slide which shows textural studies used in the assessment of the diagenetic rank from scanning electron microscopy images, with ranking of the density, alignment of clay particles developed during burial, contacts between grains, and intergranular cement formation being summed in the table there, according to the scores, to provide an indication of diagenetic rank. And in a moment or two, I'll talk about how that process, or that system of working out the diagenetic rank, was tested. Philippe Jeremias, a student from Portugal, carried out similar studies looking at the durability of a series of Portuguese Jurassic Age rocks, and he used this scheme for assess the diagenetic rank of the rocks he studied. I now want to move from mud to rock. I'm now going to talk about rock to mud. Unloading of the material results in expansion as the surface is approached, and as the surface is approached, access to air and water. Recovery of elastic strain results in expansion of the material and increase in water content. This is rapid in compaction mud rocks and slower in cemented ones, as it only occurs as the bonds are broken. Shrink swell action and the dissolution of cements will contribute to this process. Mud rocks are prone to slaking, and by this I mean that when wetted, the water traps air in narrow capillaries within the rock, and as it's dried, the removal of the water forces the air into narrower and narrower pores, such that the air pressure, because of the surface tensions of the water, surface tension effects of the water, increases air pressure in the narrow pores, and this can increase the pressure to the extent that it can exceed the tensile strength of the rock and cause it to be broken. This process of wetting and drying, therefore, is very damaging to mud rocks and will lead to their breakup, both because of the effects on the clay minerals causing them to expand and contract and this process of air breakage. Some mud rocks have undergone phases of burial and exhumation, which will introduce other structural and mineralogical changes, and we need also to take into account the glacial loading and unloading and periglacial effect during glacial periods. If we look at the effects on a cemented rock of unloading, this is illustrated here, where vertical expansion is restrained by cements and bonded grains. Depending on the strength of the bonds, this results in the formation of horizontal fractures controlled by the rock fabric. Whether by this process or air breakage, these fractures mean that water can gain access to the interior of the rock, resulting in more dissolution of cements and expansion. Because horizontal expansion is more constrained than vertical expansion, high values of horizontal stress can be created, giving rise to fissuring and deformation of over-consolidated clays and explosive rock bursts in excavations in stronger mud rocks. Once the bonding is weakened, the rock can expand by increasing water content. This summarizes the changes during burial and exhumation. The main points are the reduction in porosity and moisture content, loss of swelling clays and cementation during burial, and exhumation, which results in expansion, removal of cements, increased water content, and fracture generation. So although mud is formed eventually, the assemblage of minerals will be different from the original material. It will be dictated by the current weathering environment and not the original mud before it was buried. Continuing with rock to mud, I'll now describe work on durability. Interest in this was stimulated by problems of mud rock breakdown in coal washery plants in the 1950s and 60s, with increased mechanization of the coal extraction process. The freshly mined coal would often include rocks from above or below the seam, and these had to be separated from the coal in washery plants. The breakdown of mud rocks in these plants was a problem to their operation. Another stimulus was the generation of a flow slide that engulfed part of the village of Aberfan in South Wales in 1966. The mine waste was rock-like when it was tipped, but had degenerated into a fast-moving and very dangerous flow slide when it failed. In the 1980s, at Sheffield, I was asked to assist with the ground investigations for sewer tunnels in that city. And one of the problems they had encountered on earlier contracts was the formation of a clay slurry, which was difficult to remove from the excavations. Whereas the rock fragments could be removed on the conveyor system, the slurry had to be removed by hand in skips, which greatly delayed the tunnelling process. Roy Taylor of Durham University had noted that the incidence of problems with mud rock degradation in washery plants was related to the rank of the nearby adjacent coal seams, which suggested that swelling clays were playing a role in this. Structural flaws in the material were also leading to breakdown. In Sheffield, we carried out work on, Ian Campbell carried out work on the durability properties of a suite of 22 Jurassic mud rocks of varying composition, depositional environment, and burial depth. Samples were taken from surface exposures. The study included a comparison of the burial depths determined by adding up all the geological formations that had previously overlain the sample location with consolidation, the results of consolidation testing, which gave a value of stress at which the compressibility of the material indicated that the pressure of burial had been reached. He used the high-pressure odometer consolidation apparatus shown here to carry out these tests. We had a surprising result. The odometer test greatly underestimated the burial depth found by the geological reckoning, which was strange and unexpected. It seems that despite precautions to avoid loss of moisture after sampling, the stress relief effects had resulted in the loss of consolidation memory. He also carried out vitrinite reflectance determinations on the sediments, but these didn't provide a clear indication of the diagenetic rank, probably because of the presence of carboniferous organic material in the samples, and that would have been weathered from the original ground surface and from which the Jurassic deposits were formed. No mineralogical changes due to the diagenetic effects were apparent either, but we didn't have access to the original Jurassic sediment for comparison. This slide shows the mineralogy of the rocks that he studied, noting that those mixed layer clay smectite and illite smectite were present throughout, along with purer sort of illite, kaolinite, calcite, quartz, and pyrite in the Jurassic rocks. Changes in the clay mineralogy may have been due to climatic changes during the Jurassic. Whether calcite occurs as clastic grains or intergranular cement had a significant effect on the material. Ian also studied the breakdown mechanisms in these materials using various slaking tests, for example, wetting and drying, tumbling in water, and freeze-thaw action, and also chemical treatments that would interact with clay minerals and remove cements. The extent of breakdown was monitored by particle size analysis. He found that slaking produced gravel-sized fragments and that the breakdown into sand-sized particles was controlled by structural weaknesses in the material. Breakdown of sand-sized particles was by the shrink-swell action of weathering, the shrink-swell action of clays or mechanical grinding or impact of particles. Samples were also subjected to natural weathering experiments on the roof of the building. The product was similar to samples tumbled in water or treated with acid. Maurice Terevko also carried out slaking tests on samples using, among other tests, the standard slaking test devised by Franklin and Chandra and formalized by the International Society for Rock Mechanics. For those unfamiliar with this test, chunks of mud rock are placed in 2 mm sized mesh drums, which are then rotated in water. The amount of material retained in the drum is expressed as a percentage of the original mass of material, and the test is repeated by drying the material in the drum and subjected to a second, third, or fourth cycle of slaking. Maurice subjected his 49 mudrock samples to slake durability testing up to 5 cycles, as shown on this slide. And this distinguishes between the different durability classes of non-durable, durable, and extra durable, the very top part in green. One of the findings was that it takes at least 3 cycles to obtain a reliable result. And also, because the mesh size is 2 mm, the test is not sensitive to particles which break down into a size larger than that. It's also not very sensitive to low durability mud rocks. This is the assessment of durability using index tests I mentioned earlier. The evaluation compared the results of standard slate durability testing that I've just described with assessments based on the full characterization of the material from mineralogical and textural studies, which I described earlier. And those were compared with natural weathering experiments on the roof of the building. And those all gave very similar results, as you'll see in a moment. Various index tests were evaluated, including static slaking, point load strength, porosity, water content, water absorption, methylene blue value, fracture index, and swelling. Static slaking consists of immersing dried pieces of rock in water and observing the breakdown that occurs in 24 hours, as illustrated. As illustrated here. And the methylene blue value is methylene blue is a dye which interacts with clay minerals, with swelling clay minerals, and will indicate the presence and the amount of clay mineral in a mud rock. So carrying out those tests and then looking to combine them so that we could get an assessment of durability. And this compares the results of the full mineralogical and textural assessment, index tests, and roof weathering trials, which were all in agreement with each other, whereas the standard slate durability tests didn't really reliably distinguish intermediate and non-durable materials. In this is shown on this slide, where you can see that the slate durability test results don't agree with the full characterization and the index tests. In Chapter 36 of the ICE Manual of Geotechnical Engineering, we distinguish 3 categories of mud rocks. This is compaction mud rocks and overconsolidated clays. These are liable to undergo rapid deterioration due to the presence of swelling clays, undergo shrink-swell behaviour, and pyrite is liable to be in the framboidal form. I'll explain more about pyrite in a minute or so. And exposure to air and water will cause the material to degrade rapidly rapidly leading to a softer, cause the clay to soften greatly and for the pyrite to become oxidized, producing high sulfate acid conditions, and more about this later as well. But by rapid, I mean changes are liable to occur within the construction period. Complete breakdown of this Liassic age mud rock from near Nottingham occurred in 6 weeks. Weakly cemented mud rocks are liable to ravel into gravel-sized pieces on exposure. They may contain swelling clays and framboidal pyrite. The changes may be rapid or slower, perhaps months to years, and much faster where there's mechanical disturbance of the material. And then strongly cemented mud rocks, in which there's a pervasive cement holding the rock together, and there'll be an absence of swelling clays, and pyrite will have been converted into a less reactive crystalline form. Deterioration will be much slower over periods of tens of years and mainly controlled by structures in the rock mass. Now, Helen mentioned this in her introduction and welcome for the lecture. And I now want to tell you about the compilation of the engineering properties of mud rocks. This came about because Roy Taylor, who sadly died in 1987, asked me to contribute to an engineering group meeting in 1981. I'm greatly indebted to Roy as he alerted me to the post at Sheffield. I compiled the data from published research studies, case histories, and reports. This compares published laboratory-determined burial depths for different formations, noting that over-consolidated clays have been buried to depths of about 800 metres, whereas for rocks, burial was over 1 kilometre. The review included data on the geotechnical properties of 26 different formations ranging from Cambrian to Eocene in age. The text discussed the variations in these properties in relation to their lithology, in other words, their composition and structure, burial and exhumation, weathering grade, and the sampling and testing methods used. And they were presented mainly in this table, which you won't be able to see from where you are, but I have got a corner. But I'm sure you'll admire the skill of Pat Meller, who actually typed that on a manual typewriter. This is the top left-hand corner of the table, with data for fresh and slightly weathered and moderately and highly weathered materials, and a realistic range for the parameter, ignoring any very high or very low values reported in the literature. A reference is given for each value, so it's possible to go back to the original reference and see why that value was there. And there are notes indicated by a Greek letter for any features of the sampling and testing that should be taken into account when using those data. The number in the second column identifies the formation of the graphs in the paper. It was never intended that these values would do anything more than just alert people to the sorts of behaviour that they could expect, and certainly not to replace geotechnical testing and investigations. Further compilations, this is one of the graphs from the paper showing water contents for weathered and unweathered mud rocks and mud rocks of increasing age. Perhaps a trend of decreasing water content with geological age in the minimum water content for unweathered and the maximum value for weathered mud rocks can be discerned. The unweathered materials are shown with the solid line, and the weathered materials are shown with the dotted line. There were 2 further papers published, as Helen mentioned, for tertiary and Mesozoic deposits, and a further more comprehensive compilation including some older Paleozoic and younger Pleistocene, glacial and recent alluvial clays, was published in the clay materials used in construction in 2006. And there's also a review in Chapter 36 of the ICE Manual of Geotechnical Engineering. I now want to turn to pyrite. It's a minor but very important constituent of mud rocks of all types, from igneous and metamorphic rocks to certain glacial and alluvial deposits, and it's usually present in dark-coloured mud rocks. The table shows the approximate amounts of pyrite and carbonate in various mud rock formations. I first compiled a table like this in 1984, and this is updated. As I've already mentioned, pyrite can occur in different forms. Perhaps the fool's gold, which is here, in which it's a cube-shaped gold crystal, is quite a familiar one, but it also occurs as framboids, these things here, which are much more reactive because of the surface area that they have. They're very small, so the scale bar there is 10 microns, whereas the scale bar for the cube is 10 millimeters. And also, being dark-coloured and much smaller than you can see with the naked eye, they're difficult to identify, impossible to identify in hand specimen, and you have to look for other signs that they might be present. And they can be confirmed by, obviously, it requires microscopy or inferred by chemical analysis. This part of the talk is based on the presentation I made at the Engineering Group Conference in 2018, Keeping Lessons Alive in Engineering Geology, and the subsequent paper which was published in the Quarterly Journal of Engineering Geology, Hydrogeology. The paper presented these 7 case studies. I'm going to start with Mam Tor. They're in chronological order, basically. The first one is Mam Tor, which is a landslide. It was my first investigation involving pyrite, and it also involved the weathering of mudstone. The landslide in 1977 eventually caused the closure of the A625 road from Sheffield to Manchester. The road had been constructed in the early part of the 19th century across unstable land, which it crosses twice. It's an impressive landslide, about 900 metres long by 300 metres wide, and unlike coastal landslides, it's complete. It has a steep backscarp formed in Mam Tor beds. This is an alternating sequence of silty mudstones and sandstones. The main part of the landslide is a rotational slump, underlain by Boland shale, which is a black or dark grey laminated mudstone that contains pyrite and beds of siltstone. To the south of the area, there's limestone shown in the brick pattern on the slide. This is the superficial map of the area and a LiDAR image. There are a number of landslides on the hillsides in these valleys and elsewhere in the Dark Peak area, most of them cut through sequences of sandy beds, sandstones underlain by mudstones. The lower part of the landslide at Mam Tor is an earth flow spreading out across the valley floor, which is what you can see in the LiDAR image on the right-hand side. Studies of this and other landslides were carried out by Helen Stewart and Thanoon Aldaba at Sheffield, and they didn't have the benefit of LiDAR or even any satellite images at that time, although black and white aerial photographs were available. This slide shows the damage to the road, which, as I said, crosses the landslide area twice, the tow area, which is the earth flow, and this led to it pushed over Blackett Lay Barn, which was on the fields just beyond the edge of the landslide in 1983. This landslide is still on the move and probably will be for some time into the future. Alwyn Veer, he was a student at Sheffield University, carried out studies of the chemistry of the streams and water seepages that occur on the landslide. These were acid and contained high levels of sulfate and metals, such as aluminium, magnesium, calcium, and potassium. And there were brown deposits of iron hydroxide in the watercourses, all of which pointed to solutions formed by the oxidation of pyrite. The reactions are shown on this slide in a simplified form. The chemical formula of pyrite is FeS2, and with water and oxygen, that becomes converted into ferrous sulfate. The ferrous ion can be oxidized to ferric ion by bacterial action, and the ferric ion in solution is a strong oxidizing agent for pyrite. This means that the presence of appropriate bacteria greatly accelerates the rate of pyrite oxidation, and the oxidation process is also much faster for rhomboidal or fine-grained pyrite, as I said earlier. The reactions result in the formation of hydrogen ions, making conditions acidic, and this reacts with calcite and dolomite, that's calcium carbonate and calcium magnesium carbonate, present in the rock as cement. The result of this is the generation of calcium sulfate, which you can see the effects of that in the Bolan shale, causing it to break up, as shown on the top right of this slide. The dissolution of the carbonates also produces carbon dioxide gas, the significance of which I'll be mentioning later. The presence of potassium and aluminium in the waters reply reactions with clay minerals, and what effect might this have on the rock strength and the stability of the landslide? Alwyn found that there were 2.4 grams of sulfate per litre of water in the streams that he studied. To get that much sulfate implied that there was 1.5 grams of pyrite would be oxidized. And looking at the flow rate of the stream that he studied, that was 20 tons of pyrite per year from one stream. And in addition to the removal of pyrite, calcite cement was also being removed from the rock, and it was also being affected by selenite formation, which was causing it to break up. All geological processes going on before your eyes. This slide shows the tow area with Professor Peter Vaughan and others demonstrating that rather than where there are many seepages on this area, but rather than the ground being soft and boggy, it's firm due to the precipitation of iron hydroxide from the waters. The presence of sulfates are also apparent by white deposits on the vegetation, which you can see on a warm day. As I mentioned, there was a possibility that the presence of aluminium and potassium indicated that there were that clay minerals were being attacked by the acid, and we were interested to see whether or not this had any effect on the residual shear strength of the material and therefore affecting the stability of the landslide. This is, in order to do this, we undertook tests using a modified Bromhead ring shear apparatus in which we could change the pore water composition during the tests and measure the residual shear strength without making changes to other variables which might have affected the results. We used potassium and sodium as chemicals and also acid in order to look at these effects. The strength changed by 1 or 2 degrees, so the effect was small, but it was affected by the concentration of the ions in solution. So there were chemical effects on the strength and the stability of the landslide. Although the stability of the landslide is probably controlled by groundwater levels, these changes could also affect the stability. Thanoun al-Dabba also carried out studies on the methods of sample preparation for the residual shear strength tests and also determined the residual shear strength mobilized on slip surfaces by back-analyzing 10 other landslides in the area. The findings are summarized here. Tumbling the rock in water or treatment with acid produced a material that was very similar to the naturally weathered product. Such material gave the lowest residual shear strength, but the closest value of to the back-analyzed value was given by the tumbled samples tested in a reversing shear box. The second example concerns the reconstruction of Carsington Dam, which is situated near Matlock in Derbyshire. It's part of a pump storage scheme in which water is extracted from the River Derwent via connecting tunnels and returned there when required to augment the flow. The dam was constructed out of compacted Boland shale with crushed limestone drainage blankets, and so far as we know, no allowance was made in the design for the effects of pyrite or for the degradation of the mudstone as it was excavated, transported, and compacted in the dam. The dam is about 1,200 metres long by 30 metres high in the centre of the valley, and in June 1984, a 500-metre section of the upstream face failed. Fortunately, this is before it was filled with water. The effects of pyrite oxidation on the mudstone were apparent. The effects of pyrite oxidation of the mudstone were apparent in the drainage blankets, which were limestone, would react with acids and produce iron hydroxide and gypsum. It's been suggested that this might have impeded the function of these drainage blankets in controlling poor water pressures in the embankment. The drainage of waters from the site was acidic, sulfate-rich, and contained metals, such that it needed to be treated to control the pollution to the local stream to which it was discharged. Shear strength values for the reconstruction were based on drained triaxial shear strength tests. Bill Anderson, and Paul Osborne at Sheffield carried out a series of tests to determine the effects of acid leaching on the mudstone. Tests were carried out on the mudstone intended for reconstruction, those are labelled A, mudstone that had been leached in acid for about a month, and those are labelled B. Mudstone that was remoulded into triaxial specimens and then leached in acid. So we passed acid actually through the triaxial specimens before they were tested for strength. Those are labelled C. And mudstone which had been taken from the original dam 5 years after construction. This is the first time that this is the first and only time I'm aware of any attempt at artificially weathering a sample in a triaxial, remoulded into a triaxial sample before testing. The results of these tests showed that there was very little difference between there was very little difference between the original material and the material from the dam that had been taken from the failed dam, suggesting that over the 5-year period there'd been little loss of strength. Although we can't be sure that the samples were exactly the same. It might just be due to the variation in the materials that we were testing. The leached samples, whether that was in the bucket leaching before remoulding or the remoulded leached samples, were very similar, and they showed a reduction from the original, from the less weathered material, or the non-leached material, of about 4 degrees in the effective angle of friction, giving an angle of about 22 degrees for that material. The design of the reconstructed dam was completely different. This was constructed in a zoned structure rather than in layers, as in the previous one. Least weathered mudstone was used for the shoulders of the dam, and these are labelled S on this diagram. This was surrounded by more weathered material, which would have a lower permeability, labelled T, and the most weathered material was used for the core of the dam, because that would have the lowest permeability, labelled C. The shoulder materials had an effective shear strength of 24 degrees, but in view of the possibility of loss of strength, the design was based on 22 degrees. There were no drainage blankets incorporated into the design, and quartz gravel was used for the basal drainage layer. During the reconstruction, we carried out regular sampling of the materials being used and carried out mineralogical and chemical determinations on these materials used for reconstruction. The results were very scattered, but by looking at the average for the S, T, and C materials, we could see progressive changes in weathering. These consisted of reduction in the pyrite, although much remained in the T material. This is the material which was used outside the shoulder material. Also, the loss of calcite and dolomite cements, going from the least to the most weathered materials. Weathering accompanied by an increase in alumina with respect to silica, which is an indication of the gain in clay minerals in more weathered materials. The water-soluble sulfate values were low, and the acid-soluble sulfate generated by the oxidation of pyrite and the dissolution of carbonates rose as the weathering proceeded from S to T, and then as the material was leached, as in C material, the core, it fell. So it was high in T, having been generated from pyrite, but leaching removed it in the most weathered material. Murray Reed presented this paper at the Keeping Lessons Alive a conference, in which he catalogued 7 lessons from Carsington. Only 2 of them are listed here. One is how important geochemistry can be in engineering, as tragically 4 workmen were killed due to the presence of carbon dioxide. Remember, I said that that was a product of pyrite oxidation, as a consequence of pyrite oxidation processes. We also discovered serious discrepancies in the values of sulfate and sulfide in tests from different laboratories. All were using pretty standard procedures, but there were different preparation and testing methods, and some of them were not suitable for use with a mudstone. Care needs to be taken when using standards that they're going to be appropriate. I'll say more about this at the end of the lecture. I was sorry to find that when I visited the visitor centre some time after the dam had been constructed, there was no mention of the failure and the consequences and the reconstruction, or the problems with constructing the tunnels that connect it to the River Derwent. It would have been a great story to tell, and it might inspire people to study geology and geotechnical engineering. However, I would say we can conclude from this and other projects that they did demonstrate that, given due regard for the materials and the geological processes, a successful dam can be built out of pyritic mudstone. Case number 3. At the end of the 20th century, it was found that a number of 30-year-old bridge foundations in Gloucestershire were seriously weakened by replacement of the cement binder in the concrete by thaumasite. This is a very weak, hydrated calcium silicate sulfate mineral. The foundations were formed in excavations that were backfilled with locally derived lower lias clay, which contained pyrite. At the time of construction, the sulfate levels would have been very low, and they wouldn't have tested for sulfide like pyrite. But with exposure to air and water, the clay had oxidized, the pyrite in the clay had oxidized and produced high levels of sulfate, which had attacked the concrete. This wasn't the normal type of sulfate attack, which produces ettringite. The lack of attention to pyrite was remedied by the publication of Building Research Establishment Special Digest 1, which sets out procedures for classifying aggressive ground and the design of concrete that will resist such conditions. Various investigations into thaumasite formation and the effects of clay weathering on concrete were carried out at Sheffield and other places. One of the results was that sulfate-resisting cement is not immune to thaumasite formation, and that the presence of chloride, either from poor water or from road salt, changes the vulnerability of the concrete to damage. At about the same time, it was found that galvanised steel culvert linings on the A50 near Derby needed to be replaced. It turned out that locally derived gravels used as fill for the embankment contained pyrite, so although it would have shown low sulfate values at the time of construction, or at the time of investigation and construction, pyrite oxidation had resulted in the generation of acid and sulfate that had attacked the steel. Again, this wouldn't have been known before construction, and you wouldn't really expect such gravels to contain pyrite, but it's something to be wary of. The outcome of the investigation was the publication of TRL Report 447, which set out test procedures and terminology for assessing the effect of pyrite oxidation in materials. It sets limits on the amount of sulfur in different situations, and the limits were later incorporated into Highways Agency specifications. Seven case histories for Keeping Lessons Alive paper also considered problems with stabilised soils and earthworks, both of which can be seriously impacted by the presence of pyrite. But I don't want to go into the details here, but there are strategies for avoiding these problems. However, it would appear that problems due to pyrite have not been learned in all quarters, as you see from the from pictures on the slide. The reinforced soil wall at the top centre has deteriorated badly. It's built out of lower lias clay, and that has been seriously impacted by the by pyrite in the clay, which is corroding the reinforcement and also leading to degradation of the clay. The slide in the centre at the bottom shows the selenite crystals, which I'm just unwrapping here, kindly lent to me by Morris. And we can see that they are forming in this clay due to pyrite oxidation processes, and the clay is about the cutting that you see there, where the clay is very soft and greatly affected by weathering action, softened over a period of about a year with the growth of these rather splendid crystals. I want to just finish the case histories by talking about the problems of the use of mudstone and muddy limestones containing pyrite to support the floor slabs of buildings in Ireland. It's a very serious problem in Ireland. Up to 70,000 homes might be affected, and it might cost as much as 60 million euros to put them right. Morris and I have recently published a case study of the investigations for one particular development of 350 houses near to Dublin. This was in 2008, when the houses were only 4 to 5 years old. I would add that the possibility of such expansion was well known, with cases in northeast England, southwest England, Wales and Canada from the 1970s and 80s, reported in the literature, including by Brian Hawkins. So the problems should have been anticipated. Whether the houses were owner-occupied or owned by landlords, it is a serious problem, as mortgage companies will not lend on such defective properties. This shows the nature of construction, with a fill below the floor slab, an expansion of the floor slab leading to the cracking of walls, heave and cracking of the floor slab, sticking doors, and in one case the loss of spindles from a staircase banister. 4 houses were investigated in detail with sampling, mineralogical and chemical testing and scanning electron microscopy work. The fill was dark grey mudstone and muddy limestone, and it contained pyrite in fine-grained and framboidal form, some of it altered and expanded, the pyrite being here, framboidal, and these are expanded crystals, expanded framboids, where the products have increased the volume of the crystal, and that will cause splitting of the material, allowing access for air and water into the pyrite, accelerating the oxidation. There's also evidence of selenite being formed in these fill particles. This one here, these are the selenite crystals. Selenite is quite a soft mineral. Please be careful if you handle these later, but you can scratch it with your thumbnail, So it's unlikely that the selenite was present in the material before it was placed as fill, because otherwise, if it was present before, the crystals would have been crushed during the compaction of the fill to form the foundation. The expansion of the selenite would create cracks in the fill and provide pathways for water and air. Some people had argued that the growth of selenite would have filled pore space in the fill before causing expansion, but the growth of existing crystals in cracks requires lower surface energy than creating new ones in a void, even if this is against a confining pressure. Therefore, the formation of these selenite crystals widens cracks in the mudstones, causing them to expand. And this is greater if the particles are weak or laminated, which they are in this case. It's a weak mudstone. Chemical testing of the fill indicated that there was sufficient pyrite and calcite remaining in it for expansion to continue for a considerable length of time and to a considerable extent. So the only viable solution to this is to strip out the house, remove the floor slab and the fill, and replace it with pyrite-free rock. This is obviously a very expensive and disruptive procedure that requires the homeowner to move out for about 3 months. Concrete blocks used for the construction were also examined and found to contain pyrite-bearing mudstone. Various research studies into the expansion were carried out in Ireland and Sheffield. And this picture here shows the rig used by Amy Taylor for expansion tests in Sheffield. One of the results of this was once the reaction has started, preventing access to water doesn't stop it. I'm now going to talk about the determination of pyrite in soils, and this is where I want to finish the talk. The TRL 447 and the BRE procedures were first introduced in 2001, and both were updated with small changes in 2005. The TRL methods updated the chemical analysis procedures away from gravimetric determination of sulfate in solution using barium chloride, because this is sensitive to variations between chemists. They also used high temperature analyzer or microwave digestion in aqua regia with inductively coupled plasma mass spectrometry analysis to determine total sulfur. In other words, an instrumental method. These methods included a direct determination of pyrite and another troublesome but rarer sulfide mineral called pyrrhotite. But as the method is a fairly complex chemical procedure, it's not ideal for routine testing. And so the normal way of determining the amount of pyrite is to measure the total sulfur and subtract the amount of acid-soluble sulfur from that. Pyrite is not dissolved by the acid used for this later acid-soluble sulfate determination. So in most situations, this indicates fairly accurately the amount of pyrite. TRL provided specifications for fill for highways, BRE-SD1 for concrete, and these determinations were also used in Irish Standard 393 for assessing the expansion of fills in Ireland, and BRE Digest 552 2011 for fill in the UK. And they were all based on using these TRL methods and terminology. In 2016, it became apparent that this terminology wasn't being properly applied in some places, and it wasn't being understood. And that prompted us being Maurice Travelco, Murray Reid, Ian Longworth and I, to write these 2 papers. We drew attention to the potential inaccuracies assessment of pyrite using standard EN 1744 Part 1, 2012, because this became the standard for chemical tests for aggregates under the Construction Products Directive of 2004, and with harmonisation of standards in 2016, it became the default standard for chemical analysis of aggregate materials in the UK. This shows the comparison between those different tests. We drew attention to the differences in the methods and the units used to express the results. The significant differences are highlighted as here. Unfortunately, the 1744 specifies the use of the older, probably less accurate, gravimetric methods of determination. Many testing houses will substitute those tests for more instrument-based determinations with variable results. The drying temperatures are different, and this is liable to affect the solubility of gypsum, so there may be differences in the sulfate values. But the serious problem arises with the determination of total sulfur. Remember that this is how we determine pyrite. As the acid digestion used or specified in clause 11.1 of the standard will not take pyrite into solution, with the result that the amount of pyrite present will be seriously underestimated. Using this test will not determine pyrite, which is a serious deficiency of the standard. To overcome this, revisions to BS 1377 were carried out in 2018, and this now aligns with the TRL and BRE procedures and should be specified for characterising the chemical character of soils and rocks for construction. This does depend on an awareness of the potential for problems with 1744, given that that is the default standard. And I'd refer you to Chapter 37 of the ICE Manual of Geotechnical Engineering, which covers sulfides in construction in some detail. I now move to some conclusions. In spite of all the information about mud rocks and pyrite, we see that lessons have not been learned and acted upon in all quarters. To create problems to be overcome in later stages of a project is poor engineering, as seen by these crystals, and the fact that the materials are becoming softened. It will increase the cost of the later stages and or result in costly and disruptive post-construction remedial works being required, as seen in Ireland. The possibility of rapid degradation and sulfate generations needs to be considered early in projects in order for appropriate methods of construction and parameters for design to be used. And there are relatively simple ways of doing this. Trial embankments and the examination of exposed materials are of great benefit in investigation and assessments. Specialist testing might be required to give suitable parameters for design in some cases. Engineering works change the environment. The impact of changes to the access to air and water, groundwater conditions, and in situ stress need to be considered through the construction and design life of the structure. Changes in materials can occur in very short timescales, for example, during the construction period, and even one rainfall event could have a significant impact on material properties and behaviour. Pyrite should be considered a possibility in all dark-coloured mud rocks. You'll have heard this one before, and that is that the engineering geologist needs to be involved in the early stages of projects. Most problems are predictable, given the correct data and experience. Case histories are very helpful for avoiding problems others have encountered, and it would be good to see more based on things that went wrong that have been, where there have been solutions. A lack of attention to the behaviour of mud rocks results in avoidable and increased cost as design and construction methods are changed at a late stage or remedial works become necessary. And, as I mentioned, there can be fatal consequences. I hope what I've said will assist you in convincing people, or convincing you and others, that mud rocks matter and problems with them can be avoided if their properties and characteristics are properly taken into account in engineering design and construction processes. There are various people I want to thank. And I hope that you've appreciated this whistle-stop story of the creation, nature, and degradation of bedrocks over geological timescales, ranging from hundreds of millions of years to days or weeks. I wish to thank many people for help with this work in particular. Roy Taylor, Peter Atwell, Alan Spears, Charles Curtis, Alan Deves, Helen Stewart, Thanun Al-Daba, Ian Campbell, Maurice Trevico, Fred Bell, Martin Coleshaw, Philip Telmo Jeremias, Bill Anderson, Charles Hurd, Colin Smith, Adrian Hyde, David Holt, Paulo da Silva, Claudio Ferreira, Murray Reed, Ian Longworth, Amy Taylor, Farhat Al-Dubaka, Juma Abu Dagassam, Ashraf Abdel Kadara, Humayun Paya, Cyril Linsdale. I'd also like to thank David Whistle and my parents, Cater and Eileen Cripps. And I wish to thank especially my wife, Caroline, who's been very supportive, especially during the time that I've been preparing this lecture. There are many other friends, colleagues, and students and support staff who have also assisted me in all sorts of different ways, and I thank them. Thank you very much, ladies and gentlemen.